Alright, so we're going to start with 5 here, where we've got a library. We're loading up the shelves of a library. After some reason why all the books are on the ground, earthquake, something like that. And really, the main focus of this problem here is the idea that when you do work on something, and you change its position, what type of energy are you giving it? It changes position, potential. Remember, position, potential, position, potential. So, all the work that's done on this against the force of gravity to move these books, it's all going to go to changing their position, changing their potential energy. So, in your Y here, it'd be very good to show that you know that potential energy is the energy of position. All right, and that probably to change the book's position. The book's position work is done against gravity. Thus, it's going to be PE grav. What's the other type of potential energy that we've talked about? Is it an E or an F? Huh? Nobody? Good thing we're doing the lab tomorrow, all about it. Yeah. Exciting. Probably the most common mistake here is in the details of this problem. And Ed and I were just talking about this. Did it work, Ed? It did work, good. And the details of this problem are that if we take this bottom line here as the floor, our first shelf is here at 0.1 meters up. Our next one is at 0.4 meters. Our next one, let's make sure. Space 30 centimeters. They start at 0.1, and there are 5 shelves altogether. So 1, 2, 3, 4, and 5. And so this one would be at 0.7 meters. This one would be at 1.0 meters, and this one would be at 1.3 meters. Most common mistake is to forget that the books are going from lying flat, they're being moved up to standing on the shelf. Which means if we look at their centers, they've gone from basically on the floor to standing halfway up on the shelf. So the center of this book isn't at 0.1 meters, but it's at 0.1 meters plus 0.21 over 2 meters. Because that's the height of the book. The top of the book would be at 0.1 plus 0.21. And so this is what? 0.205 meters. So, and then the book, we can do that, we can think about that on each of these shelves, where the centers are. That's where we can estimate, or we can average out, because it's going to take one bit of work to get the bottoms to the shelf. It's going to take a different amount of work to get the tops to the shelf. If we say all of it is at the center because the tops and the bottom average out to the center, then we only have to worry about the centers. So now this one would be at 0.505 meters, 0.805 meters, 1.105 meters, and 1.405 meters for the different shelves. All right, so that's probably the most common mistake, is to forget that little, almost trivial bit, but it makes a big difference. Potential energy, gravitational, is going to be the weight, mg, and the change in height. That it is the change, the way the positions change is the change in height, gravitation. So, for each shelf, we would have the PE grav of a single book. So like PE grav, we'll call that for shelf 1. And you move 25 books there, so it's 25 times that equals the energy total for shelf 1. And then the same thing for shelf 2 and 3 and 4. And when you get all the way down the bottom here, you add those up. Total 2 plus energy, total 3 plus ... and that gives you your total energy here. All right, for the whole thing. So, like for the first one, you do 25, and in here you're going to have mg h1. That's going to equal energy total 1. And and now it's just a substitution in. They tell you m, you know g because you know what planet you're on, and h1 is going to be that 0.205 meters that we just discussed. It's going to be h1. So, common mistakes will be to forget that you're lifting 25 books to each height, or what I talked through with the actual height that you lift the middle of the book to. Alright? And now just add them all up and find it for shelf 1, 2, 3, 4, and 5. This, of course, is shelf 1. That's 2, that's 3, that's 4, and that's 5. And then when you add all those up, you get the total energy. Let me know if you need help individually on that one. Alright, so we're going to go on to number 8. And we got this toy gun doing the Nerf pellet horizontally. Ooh, if it's moving it horizontally, why are they telling us that? What do they want to take off the table? Gravitational potential energy. They want to tell you that don't even bother to mess with that because it's not going to matter. It's only vertical motion matters with gravitational potential energy. And then it tells us about friction, which right away well, they tell us about a spring. So I started thinking, oh, elastic potential energy. Then they tell me about a frictional force, and oh, friction is one of those non-conservative forces. In other words, it doesn't keep the energy about motion. It makes it into other types of energy, whatever work it does. And then, again, I'm back to looking at the spring, thinking about potential elastic energy, and then, oh, speed. Right away I think about kinetic energy. And so now I'm kind of putting that all together in my mind, and I get to my Y here. Let's see, this is number 8. And I think, okay, I'm going to start off by the friction does non-conservative work, so mechanical energy is not conserved in the system. I better make sure I'm clear what my system is. Let's see, the system would be the gun, spring, pellet. They call it is conserved in the system. Remember, that word mechanical doesn't refer to, like some machine, it refers to about motion. All right? So we're saying that not all the energy stays about motion, but the energy is constant throughout the system. It'd be good to also recognize that potential energy, elastic, or spring, however you want to say it, is about the position of the spring. Show you understand that. And that kinetic energy is about speed. I had been up until about yesterday using kinetic energy is about motion. I think it's clearer if it's about speed. Because motion has to not only how you're moving, but also your position. So kinetic energy and potential energy are both types of mechanical energy because they're about motion, but it's kinetic energy that's energy about speed, about how you're actually moving as compared to just what your motion is. So I'm hoping that's clearer to people. So that why should lead me right into my how here. Very specifically, energy of the system is conserved. So that means the energy I have at the beginning of the system will equal the energy I have at the end of the system. And then it's important, well, what's in that system? We have the gun. We have the spring, so PE of the spring would be a good thing to have in here. We have the pellet, which would have kinetic energy. And then afterwards, we still have the spring, right? We still have the pellet, but there's a difference, so we put primes on them. And we know that we encountered friction, which did non-conservative work. All right? So if I look on my equation sheet, the potential energy of a spring, the energy due to its position, is 1/2 kx squared. How much kinetic energy is the pellet going to have when it starts, before it moves? 0. So that's going to be 0 joules right away. Once the spring has fully expanded and it's pushed the pellet down the barrel, how much energy is it going to have still as energy of position? 0. Plus 1/2 mp squared plus the work is force and distance. And that we said it was friction doing that. So I believe they give me K. I believe they give me X, right? Let's see. Spring, okay, they give me, there's the mass, the inertia of the Nerf pellet. It's in grams though. Should I use it in grams? No, convert it to kilograms. There's my spring constant, K. Spring constant is 8.5 newtons per meter. The barrel of the gun is this long. So that's the distance that my frictional force can act on it. But I need to convert that to meters. Constant frictional force given to me. If the spring is compressed 5.1 centimeters, remember the X here in our potential energy of the spring is the change in position of the spring, how much it's compressed or expanded. So they've given me K, they've given me X, they've given me M, they've given me F, they've given me D, and they're looking for V. So I have the whole relationship there, and all I need to do now is the math. If you need help individually on the math, let me know, and I'll be glad to come around and help you. All right, so number 6 here with our elevator cable breaking, and the elevator is going down. It's above a huge spring. And this is actually, if you ever look at an elevator shaft, there is usually a huge spring underneath them as a safety measure, so that if the cable ever breaks and the automatic brakes ever and also fail, that you won't splat. You'll slow down, so hopefully. So they want to know the work done by gravity on the elevator before it hits the spring, speed of the elevator just before striking the spring, and the amount of the spring compresses. Note that work is done by the spring and gravity for this part. So, I would start off with things like the work done by gravity is due to the weight of the elevator. Probably also we want to state that the elevator gains kinetic energy due to this work. And then probably the last statement, so this is important and this is important. The last statement to be really important is the kinetic energy of the elevator at the bottom is changed sorry, I'm going to reword slightly. The kinetic energy of the elevator at the bottom and any additional PE grav are changed to PE elastic of the spring. I think, and for me, what I need to do is I need to draw a picture to help me better keep track of everything in this. So, picture I'm going to draw, let's see. We'll start, we have our elevator up here. Going to go down until it hits here. At this point, it's going to hit our spring, but it's going to keep going down until it's finally rests down here, with our spring all really compressed below it. So it's going to have work done on it by gravity there. It's going to have kinetic energy here. When it gets down here, it's going to have potential energy elastic. That's the height it gives me. This here I'm going to call delta x. The height, the amount it compresses the spring. All right. So for number 1, for part, do they number them or letter them? Letter. Okay. So for A, the work done on it is the force and the distance, right? So the work done by gravity is going to be the force of gravity, mg, and that distance it works through h, right? For B, how much kinetic energy it has, well, whatever work it did by gravity is going to go into its kinetic energy at the bottom. So that's going to be the same exact answer, right? Do they want to know how fast it's going? Yeah. Okay. So I've got that work due to gravity, 1/2 the inertia of the elevator, and then its speed at the bottom, and square that. Yes? Those are the pretty straightforward parts, right? And then part C is the trickier part, because in part C we could also approach it that energy is conserved in this whole system. So what I'm going to do is say, okay, well, right at this point, right before it hits, as it just gets to the spring, it has this kinetic energy at the bottom that it had at the bottom, and then when it compresses the spring, and as it compresses the spring, it releases, or it changes potential energy. That change in potential energy, and all of this has to be taken up by the spring. So that's that last statement. The kinetic energy of the elevator at the bottom and any additional potential energy of gravitation are changed to a last potential energy of the spring. So it not only has some energy because of the work done on it by gravity in the form of kinetic energy, it also changes its position more, so it gets rid of more gravitational potential energy, all that going into the spring. So kinetic energy at the bottom is a value that I have from part B, really, or part A. This is going to be its weight and the change in height, which will be our delta x. And then over here, remember it's 1/2 the spring constant k, and then we'll have delta x squared. And it's delta x that we're looking for. All right, so work is done, gives it kinetic energy at the bottom. It has that kinetic energy as it touches the spring. Then as it compresses the spring, that kinetic energy and the additional potential energy, gravitation that's changed by it moving downwards further, are both given to the spring to change its position. All right? Let me know if you need any help individually on that one, and or if you get stuck at all on it.